In the last lesson we started talking about what limit statements mean, and we talked about the notion of an envelope. In this lesson we're going to be talking about limits of functions of a real variable, and we're going to discuss the idea of what we call neighborhoods. Let's look at a sequence and just review what an envelope is. Here's a sequence that's represented by a graph, and this sequence has a limiting value that we'll call L. So we'll say the limit as n approaches infinity of a sub n equals L, where L is plotted on the vertical axis. And what that means is that the values of the sequence get arbitrarily close to L. They get within an arbitrarily small distance epsilon of L. So here's a picture of an envelope of size 2 epsilon that goes above L and below L. It's centered on L. And you can see that no matter how small epsilon is, there's going to be some place, which we designate by capital N, such that everywhere to the right of that place, the red dots are inside the envelope. That's what this says symbolically. It says, for any positive number epsilon, there exists a value of n such that the value of the sequence is within the envelope of size 2 epsilon whenever we're to the right of capital N. And by the way, I'm defining capital N a little differently than my last lesson. In my last lesson I said little n is greater than or equal to capital N. In my last lesson, capital N was the first point that was inside the envelope, and in this lesson it's the last point that's not inside the envelope. It's a very minor difference, but I'm going to use a greater than sign from now on because that's more standard. I'm also going to use a less than sign here rather than a less than or equal to sign, but it doesn't substantially change the definition. And this summarizes what we mean by limit statements involving sequences. But in this lesson we're concerned with limit statements involving functions of a real variable. So to move toward that, I want to start with another sequence. The sequence cosine of 1, cosine of 1/2, cosine of 1/3, and so on. You can probably recognize the pattern of this sequence from the first three terms, but if you're really clever, you should be able to state the expression for the general term, which is cosine of 1 over n. But the more interesting question is, if you know the expression for the general term cosine of 1 over n, can you figure out what the limit of the sequence is? And that might seem like a complicated question, but I want you to see that there's a kind of nice intuition you could use. When you look at a sequence whose pattern you know, think about what if you continued the sequence way out. Then you look at numbers like cosine of 1 over 635. 1 over 635 is a very tiny angle, and the cosine of tiny little angles should make you think of the cosine of 0, and that will let you realize that the limit must be 1. It simply is cosine of 0. That's a kind of intuitive way of seeing what this limit should be without really proving that the limit is 1. Once you have learned how to rigorously prove limits and you've learned some theorems about limits, you could say things like the limit of a cosine is the cosine of a limit, and the limit of 1 over n is 0, so cosine of 0 is 1. But what you're doing intuitively right now is exactly equivalent to the rigorous reasoning that I've just shown you. So to help lead us toward limits of functions of a real variable, I want to investigate this statement, the limit as n approaches infinity of cosine of 1 over n equals 1. And we're going to look at a graph that represents the sequence graphically, but not the same graph we looked at before. We're going to look at a graph that plots y as a function of x for the curve y equals cosine of x. Then if we want to represent this sequence on the graph, we plug in n equals 1, and we see that a sub 1 is the y-coordinate that's plotted on the y-axis there. And when n equals 2, we have cosine of 1/2, identify the location of 1/2, and a sub 2 is this y-coordinate up here. And we could continue with a sub 3, which is cosine of 1/3, and so on. And we get a sequence of points plotted in red that all lie on this curve, and you can see that the y-coordinates form a sequence of numbers that is approaching 1. And you can tell it's approaching 1 because you understand the property of the cosine curve. So I'm going to underline this limit statement in red, and we can see that this limit statement is reflected in the behavior of the red dots on this curve. I can come up with other limit statements, like this one that I'm going to underline in blue. That's a reflection of the behavior of these blue dots over here on the left, and I can come up with a third limit statement that I'll underline in green. That's a reflection of the behavior of these green dots on the right. And you could imagine there's an infinite number of different limit statements I could come up with, all of which are equal to 1, and all of which are a reflection of an underlying property of the curve y equals cosine x. And that property can be itself stated as a limit statement, and that statement is the limit as x approaches 0 of cosine x equals 1. Now this is the type of limit statement that I would like to rigorously define now. The limit as x approaches 0 of cosine of x equals 1. Once again, this limit statement has to do with getting arbitrarily close to 1. It says that the cosine curve gets arbitrarily close. In other words, it goes inside an arbitrarily small envelope. So here's an envelope that surrounds the number 1. It goes from 1 minus epsilon to 1 plus epsilon, where epsilon is some arbitrarily small positive number. And we want to say that the cosine function goes inside of that envelope and stays there everywhere in some region we call a neighborhood around x equals 0. So the purple shaded region represents a neighborhood. And you can see that in that neighborhood, if we restrict ourselves to looking only in that neighborhood, all of the y coordinates of the curve, which I'm showing you in red, fall squarely inside the envelope. So this limit statement means that for any arbitrarily small envelope, green envelope, there exists some neighborhood, the purple neighborhood, that keeps the curve inside the envelope everywhere in the neighborhood. And the neighborhood is characterized by a number that we call delta. This is just another Greek letter. Remember we were using epsilon before. This is a lowercase epsilon. There's also an uppercase epsilon, which looks just like our uppercase e. Well, delta is just another letter in the Greek alphabet, except you might be more familiar with the capital delta, which is a triangle. Now let's look at a more general picture of a function. Here's a function called f, which has the property that the limit as x approaches a of f of x equals L. And we want to state rigorously what we mean by that. We mean that the function f gets arbitrarily close to L, that is, it falls inside an arbitrarily narrow envelope that goes from L minus epsilon to L plus epsilon, anytime you're in some neighborhood of A. That is, no matter how small you make that envelope, you can find a neighborhood that runs from A minus delta to A plus delta, such that the y coordinates of the curve everywhere in the neighborhood fall squarely inside the envelope. Now I want you to notice that if I chose a larger neighborhood, I wouldn't fit inside that envelope. So the limit statement is saying for any arbitrarily small epsilon, there exists some neighborhood for some small enough delta such that in that neighborhood the function is contained inside the envelope. Now let's talk about how you would describe that neighborhood mathematically. We're talking about an interval of values of x. So if I plot them on the x-axis, the plot looks like this. That's a picture of an open interval. And in terms of inequalities, we have the inequality a minus delta is less than x is less than a plus delta, which then could be manipulated. You know, if you subtract a from all three sides of that inequality, you get negative delta and positive delta are bounds for x minus a, which then could be written using absolute values. And that's a nicer way to write it, because that basically says the distance from x to a, how far away x is from a, is less than delta. And that's a nice way to describe this region around a. It's symmetrically about a. However, we don't really want this definition, because there's a complicated case that we haven't considered. And that is the case where we have a function for which the value of the function at a is different from the limiting value L. That's a jump discontinuity. We want this case to still be described by the same limit statement because we want a limit statement to describe the behavior of the function around a without saying anything necessarily about what actually happens to the function at a. So we're going to define our neighborhood slightly differently. Instead of the neighborhood absolute value of x minus a is less than delta, we have to modify it, because if I shade in for this function all of the parts of the curve inside that neighborhood, you'll notice that I have something sticking outside of the envelope. So we're going to define our neighborhood slightly differently. We're going to define our neighborhood by excluding x minus a equals 0. If I were to shade that on the x-axis, it would look like this. It would have holes on the ends and also a hole in the middle. And now, if I shade all the parts of the curve in this neighborhood, you can see that every point I've shaded is held inside the envelope. So this is actually the way we're going to define neighborhoods. Neighborhoods are like open intervals with a point removed from the middle. To summarize, the limit as x approaches a of f of x equals L means no matter how small we make the envelope epsilon around L, there will always be some neighborhood delta around A small enough so that at every point in the neighborhood the value of the function is inside of the envelope. Symbolically, if we want to write that in symbols, we would say the limit as x approaches a of f of x equals L means no matter how small we make the envelope, that is for every possible positive value of epsilon, no matter how small, there will exist some neighborhood size delta such that the functions inside the envelope, that is the distance of the function from L, is within epsilon whenever we are inside of the neighborhood. 0 is less than absolute value of x minus a is less than delta. This is the definition of the limit as x approaches a of f of x equals L. And you could see it's something that will take some time and some practice to get used to. Don't expect to just read it and understand it right away. So one of the ways we'll practice it is we'll look at a specific case. The limit as x approaches 2 of x squared equals 4. This is something you could probably guess intuitively. And we're going to have two people, just like in the last lesson, we're going to have two people argue. We have some smug guy who makes the statement limit as x approaches 2 of x squared equals 4. And then we have a skeptical guy who questions that. He says, you think x squared gets arbitrarily close to 4 as x gets near 2? And the smug guy says, yeah, absolutely, arbitrarily. So the second guy says, well, for example, then can x squared get within 0.0387 of 4? 0.0387 is an envelope size. It's a value of epsilon. He's throwing out a challenge. Graphically, this is an envelope. Let's say that represents 0.0387. He's asking, can you find a neighborhood that guarantees that the function x squared will stay inside of this envelope around 4? And the guy says, well, yes. If, for example, if you put out the challenge epsilon equals 0.0387, then I will meet that challenge by saying set delta to 0.008. Now I'm going to show delta equals 0.008 on the graph. That would be everything from 2 minus 0.008 to 2 plus 0.008. And if you look very closely at the graph, you'll see that the y-coordinates of the curve everywhere in this neighborhood, delta equals 0.008, really do fall inside of the envelope that he challenged him with. And the way you say that using mathematical language is for all values of x such that 0 is less than absolute value of x minus 2 is less than 0.008, the function f satisfies absolute value of f of x minus 4 is less than your proposed value of epsilon. Now let's keep track of this. We'll make a little table, and we'll say that for this first value of epsilon that was thrown out, the challenge was met by the value of delta that was given in reply. So now the challenger thinks, well, maybe I gave him too easy a challenge, and he comes up with an even smaller value of epsilon. He says, what if epsilon is 0.000296? Right, graphically, that's going to look like a smaller envelope. Here we'll modify it in the picture. So there's a new epsilon. It's smaller, and you can see that the neighborhood that was given with delta equals 0.008 no longer suffices. The challenge, however, is met with delta equals 0.00006. Here's a picture of the new neighborhood. We make it small enough so that everywhere in that neighborhood the function does stay within the envelope. And then we put that as a new entry in our table. And the discussion continues, and every time the challenger comes up with a new value of epsilon, a value of delta is found that satisfies the requirement. So eventually they get this table of values, and you can actually confirm for yourself on your calculator that these values of delta do give you a sufficiently small neighborhood for each of the values of epsilon. You might, just to make sure you really understand this, you might want to pause the video at this point and try it on your calculator. Verify that each of those values of delta will work for the corresponding value of epsilon. Now, to really prove that the limit as x approaches 2 of x squared equals 4, it doesn't suffice to show that for 4 values of epsilon you could come up with a neighborhood-sized delta. You have to show that for any epsilon, no matter how small, there would be a value of delta. So the skeptic on the left is having trouble disproving the limit statement, and he starts to wonder if the guy on the right has some kind of formula, and he thinks, I wish I knew what this guy was thinking. If I could read his mind and understand, maybe he has a formula that he's using to come up with a delta for each epsilon, and he does. He's simply taking the epsilon values and dividing them by 5. When the challenger realizes this, that there's a formula and there's going to be a reply to every challenge he throws out, no matter how small, and at that point he finally believes, he knows that the limit as x approaches 2 of x squared really is 4, because for any epsilon, no matter how small, there exists some value of delta that satisfies the challenge. So if you followed that story, maybe that makes it a little easier to understand the statement that is the definition of the limit. We'll state it one more time for this specific case. The limit as x approaches 2 of x squared equals 4 means for any positive epsilon there exists a delta such that absolute value of x squared minus 4 is less than epsilon whenever 0 is less than absolute value of x minus 2 is less than delta. And we know there exists a delta for any epsilon no matter how small because delta equals epsilon over 5 works. Now I've claimed that delta equals epsilon over 5 works, but I haven't shown you why it works. For homework, I want you to come up with this yourself. Your homework assignment is prove that the inequality statement 0 is less than absolute value of x minus 2 is less than epsilon over 5 implies the inequality statement absolute value of x squared minus 4 is less than epsilon. Prove that the first inequality statement implies the second for any positive value of epsilon, or for any positive value of epsilon less than 5 actually. And if you can prove that, then you have essentially proved that the limit as x approaches 2 of x squared equals 4, and you should congratulate yourself.